In last 5 lectures, I have discussed and we have seen the methods for solving the system of linear equations. We have the applications, and we can see there are many applications of the linear system. Solution by Gauss elimination, Gauss-Jordan, row echelon form, reduced row echelon form. Definitely when it's a big system, then you are not solving on a table. You have to write the program, and then we get the numerical linear algebra for this purpose. But anyway, I give you the short example so that you're able to know that how we are going to apply our methods which we have developed for that one. I have taken one example for you. That is the example for the curve fitting. So we are having a parabola. And the parabola, we have the equation for parabola, where y is equal to ax squared plus bx plus c. This is an equation for parabola. And we are having the values unknown is passing through certain points. It's a quadratic equation. So when we want to get the values with the known unknown values will be here a, b, and c. They are passing to the point x, y, a, b, c, and there are 3 variables which we want to find. When we want to find three unknowns, then we must have 3 equations. If we want to have the 3 equations, means we must have 3 points. You have the equations like this one, y equal to ax cubed plus bx squared plus cx plus d. Now, how many points we are having? To get the equation, this one, passing through the points, we have 4 equations. 4 values, a, b, c, and d. It means we need here 4 equations. It means we need 4 points. I come back to this one. We need 3 points, and from 3 points we get 3 equations a, b, c, and we solve it. And getting the value of a, b, c, substitute it. We get here the curve which is passing through the points and represented by the parabola. So we have written the example for you. Suppose that the points -1, -2, -1, 2, and 1, 2 lie on parabola. Our parabola is y is equal to a plus bx plus cx squared. We want to, number 1, determine an linear system for equations in 3 variables a, b, c, and find the equation of parabola. So we're having here 3 points. We can find the equation for each point lying on the parabola. So we can say here, number 1, we can have the solution of this one, where the point is x equal to -2 and y equal to -1. And this point we get the equation for this one, putting x equal to -2 and y equal to -1. Put here, we get here a minus 2b plus 4c equal to -1. Then we get here the point, our next point is x equal to -1 and y is equal to 2. We substitute in our equation, we get here a minus b plus c is equal to 2. Then our third point, here is our first point, second point, our third point. Third point is x equal to 1 and y equal to 2. I substitute in my parabola, I get here ax, a plus bx, bx is 1, b plus c, that's x is 1, we get here c, and is equal to 2. So we get here the first point, we get the equation. Second point, we get the second equation. Third point, we get the third equation. And we can write here our system of equation is a minus 2b plus 4c is equal to 1. Second equation is a minus b plus c is equal to 2. We get here a plus b plus c is equal to 2. So we are having here this is equal to -1 and this is equal to 2 is equal to 2. So this is our linear system, and we can solve this linear system. And this is number 2. We have the solution of the linear system. We write the argument matrix form, and we remember that our variable in this case are a, b, and c. So I write here a, the matrix of coefficient. I write here capital B because small b is coming as a variable. And I write here my a, that is here 1, -2, 4. I get here 1, -1, and 1. We have 1, 1, and 1. And we get here the right hand side is -1, 2, and 2. So I'm not going to solve it. We have solved the example, and we get here the reduced fraction form. This is 1, 0, and 0. We get here -2, 1, and 0. We have 4, -3, and 6. And the right hand side we get here reduced form 1, 3, and minus 6. So we are using Gauss elimination method or row echelon form. We write this system in our equation and then we make the substitution. I get here A minus 2B plus 4C is equal to minus 1. We get minus B minus 3C is equal to 3. I get here 6C is equal to minus 6. So I divide by 6. I get the value of C is equal to minus 1. I get here minus B is equal to 3C plus 3, and C is equal to minus 1, get minus 3 plus 3, that's equal to 0. I get the value of A, so my value of A is equal to, my value of A is minus 1 plus 2B minus 4C, substitute the value, we get minus 1. The value of B is equal to 0, so get it plus 0. Value of C is equal to minus 1, we get here plus 4. And the value we get here 3. So get the value of A is equal to 3, value of B is equal to 0, and value of C is equal to minus 1. I substitute my equation and get the equation of parabola. So my equation of parabola is y is equal to A is 3, plus bx, b is 0, and then we're having minus x square. So this is my equation of the parabola. This is how we can apply our method to get an equation, which is the equation, quadratic equation, representing the parabola. We have 3 points. What we get, we substitute the points in our equation, and we get here 3 equations. My equation 1, this is my equation 2, and this is my equation 3, and this is my linear, and these are my system of linear equations. And in this system of linear equations, I'm just going to, this here is my equation 2, and this is my equation 3. So I solve these 3 equations and get the value of A, B, and C. I use here Gaussian elimination method. I can use Gauss-Jordan method also. And we can write the elimination, and then we write the system of equation, the second part. And then we are having here the substitution and get the value of C, get the value of B, we get the value of A. And substitute the value of A, B, and C here, we get the value of Y. We take application for the electric circuit. In electric circuit, we just define the rules we are going to use to develop our system of equations. As you have seen in the last example, we are having the curve fitting. And in curve fitting, we are having here, this is the curve, and these are the points, they are passing through the curve. This is the rule on which we develop our system of linear equations. But here, we have electric circuit. In electric circuit, we are having 2 rules, the Kirchhoff law, the voltage law, and Ohm's law. And Kirchhoff law says that the total voltage in the loop, the drop of the sum of the voltage in one direction is equal to sum of the voltage source in the same direction. So we're having this as the circuit, and these are our resistance. This is our voltage V1, V2, V3. That's a drop in the passing through the resistance, and then this is our source. That's V4. So we say the rule says V1 plus V2 plus V3 is equal to V4. Now then we're having the rule, the second rule which we apply for getting the system equation. This voltage is equal to IR. I is our current in ampere, R is our resistance, and V, as I said, the voltage drop across the resistor. So we use these 2 laws, and we write our system of equation for the circuit. A circuit can be a very big circuit, but we are taking, for example, a small one, Swan loop, so that we can understand how the method is working. So I have written an example for you for the electric circuits, and we can see it how we can just calculate the current moving in each circuit. When we have 3 circuits, 3 loops we are having here, and we have these the batteries, and this is our resistance as I shown you before. And here we say the current is I1, this is I2, and this is I3, and this is the direction of the current. We can see it is moving to this direction also. Here it is moving to this direction. Here it's also moving to this direction. So we can see here when we take from negative to positive, this value is voltage is positive. When we take here this from positive to negative, this becomes negative. So in circle we say the resistance we're having here, this is our resistance 4I, that's as shown you, this 4I1, and this also again here positive 4I2, 4I1, and then here 3I1. So we get the total 11I1. Now the impact of this I2 in this circuit is, this is opposite. In this circuit, the current is moving from in this direction, and here, when we take this one from impact of I2, this is the opposite direction. So when we say here, this is positive 11I1, and here we get minus 3I2, and we have the voltage. The voltage here, the battery is 30 volts, is the direction from negative to positive, so we take as positive. So our first, the loop, in the first loop, the current is given by this equation 11I1 minus 3I2 and 30. This is our first equation. We come to the loop 2. Again, we look on the loop 2. This here is positive. So this will become, with reference to this loop, coming from this side is positive, and here is opposite side that become negative. So when we take this impact of this resistance for I, so the for current for this one is here positive, this 3, and here plus 1, we get here plus 1, and then also this one, and we get here 6I2. But here in this case, this is opposite to that one, so we get minus 3I1, and here in the case of the third loop here, is again minus I3 multiply 1. So we get here three values for I2, impact of I1, and impact of I3. We come to the last one, the third, and we get here the equation minus 3I1 plus 6I2 plus minus I3 equal to 5. This is my second equation. Now look on the third equation. There is no impact of I1, as there was no impact of I3 in this circuit. It's not connected with this one. It's connected with the I2. So here, the current we have taken this one. This is minus 2. From negative to positive, we get here plus 5. So that's why we have written here 5. Now, if we look on this loop, this going from positive to negative, this become minus 5. Also in this way, this negative, positive to negative become minus 20. So the total voltage will be minus 25. So here we can see this is 1, this is 1, this 1. We get 3I1, this is positive. And this is opposite this direction with I2 in 1 ohm, they become negative. So get here minus I2 minus plus 3I1 is equal to minus 22. I have told you minus 22 because the current in this loop is from positive, and from positive to negative, that's minus. Here from negative to positive is plus, from positive to negative is minus. So we are having there three equations, E1, E2, E3. This is my E3. We rewrite my equation as system. The system of linear equation I get here, 11I1 minus 3I2 is equal to 30, minus 3I1 plus 6I2 minus I3 is equal to 5. And I get here minus I2 plus 3I3 equal to minus 25. So I want to solve this linear system. Main in the discussion in this part of our example is to formulation of the problem. That's how we can formulate a problem for the electricity. There's only 3 loops. We can have 100 loops. And we can write the equation for 100 loops, and we can solve it with the help of numerical linear algebra. Now here we have this one. We write the augmented matrix form, and we solve this one for the unknowns I1, I2, I3. We get the reduced row echelon form or Gauss-Jordan method. They give me the value of I1 is 3, and I2 is 1, and I3 is minus 8. Here minus 8 means in the loop the voltage is on the opposite side, from positive to negative. That's here the voltage V3 will be, I3 will be there. The opposite side, another direction given to this one, that is minus 8 is showing that one. So that's the example again. My purpose for showing this example was to tell you how to formulate the system of equation, and this is our system of equation. We get here 3 loops. I have the currents is I1, I2, I3. As I told you, we can have a very big loop, and we may have the currents the loop to 100, and we can write the equations for that one. And this is how we can write the equation. We use the Kirchhoff law, and we use the Ohm law, and we can write our system of equations. So we take an example for the temperature distribution as an example. We have done first the cover fitting, then we having the electric circuit. We have the temperature distribution. This is the plate, and the plate is perfectly insulated on top and bottom. So there is no flow of heat from bottom, but on the sides we have the temperature kept on 50 degrees centigrade, 30 degrees centigrade, 50, and 0 degrees centigrade. So we want to estimate the temperature distribution inside the plate at the point T1, T2, T3, T4. It can be more points. It can be 100,000 points. They were very big system on which we are going to check the temperatures. The idea will be the same. So actually we are having the temperature distribution given by the steady state. There is no change with respect to time by the Laplace equation, partial 2 by t by partial x square plus partial 2t by partial x square. Here we get partial t by partial t, and that's cancelled because not changing with time. We use here explicit finite difference method, and we change this one into the linear equations. The rule is this, that we take here this 4 times t1 is equal to tw, t west, t east, t north, and t south. So we just take this one. This is the rule. With the help of this one, we get the equations. We can check here this point at t1. This 4t1 will equal to 50 plus 30 plus t2 plus t3. The second equation at t2 will be T1, 30, 50, and T4. At T4 will be, at T3 will be equal to 50 T1, T4, and then it is 0. And at T4 will be T3, 50, 0, and T2. So we can see it here. We get this equation, and we can just simplify this one. This equation multiplied by 4. We get here 4 T1 plus T2 plus T3 is equal to 50. This is my equation 1 at the point T1. Then we have equation 2 multiplied by 4. We get here, we take this, sorry for this one, this T we take to the other side, and this become here minus. Take to the other side, we get here T1 with minus sign, plus we having 4 T2 minus T3, and then we keep this 50 on this side, that's equal to 50 plus 20, 30, that will be 80. That's my E2. Now here again we multiply by 3. We get here 4 T3. We take T1 to this side, we get here minus T1. So this become here plus, and here minus T4, and this equal to 50. This is my equation 3. We just apply the same rule. As I mentioned that we having the west, east, north, and south, and multiply here by 4, and we get the equation. Again we multiply here by 4. We get here 4T4. And then we take this value to the other side. This is minus T3. This become here plus, and this take to the other side minus T2. And here 50 plus 0 is 50. And we are having here, this is my equation 4. So we can have here correction, because here 50 plus 30 is 80. So I can write the augmented matrix form. I write my A, and I write my B. And then I'm having here, my system is here 4. We're having minus 1. We have minus 1, and we're having 0, and here you get 80. So similarly, I write my equation 2. Equation 2 is minus 1, here is 4, then it's minus 1, 0, and then we're having here again 80. And third equation is minus 1, we get here 0, we get here 4, we get here minus 1, we get here 50. And my next equation, last equation is 0, we get minus 1, we get minus 1, we get here 4, and get here 50. So this is my system of linear equations, and I can apply my Gauss elimination method or Gauss-Jordan method, and one of the method, row echelon form, reduced echelon form. I solve it, I get the value of T1. T1 is equal to 36.25 degree, and then you have the value of T2. T2 is 36.25 degrees, and we have the value of T4, T3. This is 28. We're having here this equal to 28.75 degree, and then we're having T4 also is equal to 28.75 degree. This is the idea actually, that how we can use our system of linear. We can write the system of linear equation E1, E2, E3, E4, and then we can write the augmented matrix form, and we can solve augmented matrix form, and we get the distribution of the heat at the point T1, T2, T3, and T4. This is actually the idea. Again, we're having the distribution in a plate, a metallic plate, and this plate is square and perfectly insulated from bottom and top. And we use the formula for solving this one, that at the point T1, the 4 times T1 is equal to on the left, right, up and down, and we write the equation. This one equation for the point T1, T2, T3, T4, and we solve it and get the value of T1, T2, T3, T4. This is the idea, and as I said, we're taking a small example, but we can make it a distribution at a very high level. We can have thousands, millions points on which we want to do. Again, we use here numerical linear algebra when we have the large system of equation to solve our problem. So I'm just going to give you the very important example. Is a practical we are using in our life. That's the traffic flow. And the traffic flow, we want to understand how much flow traffic is coming in and how many coming out at the point. And then the traffic people, they used to make the plan that how they can control the traffic. So important rule for the traffic network is the traffic inflow at a junction is equal to traffic outflow. That's the rule which is being applied to find it. For example, we're having from the right about 60 cars are coming in and they are going out. We don't know how much going to this side and this side. So say at this point we can have 60 coming in and these are coming out, that will be x1, x2. So 60 is equal to x1, x2. This is a conservation law. It's used also in nature. In many problems we use this star to solve our problems. So here in the case we're having 4 roads, they are combined at the point, and there this inflow is from the left and also from down, and we have from the south, and from the east we have the inflow, and outflow is towards west and towards north. So we having this inflow 300 plus 200. This is our inflow is equal to x1 plus x2. So this gives me the equation. This is how we can find the equation at the point every network. So I give you here the practical example of the road network. There are 4 roads we are having in the picture, and they are the junctions at the point A, B, and C. The flow is coming in at the point A and going out also. At the point B, this is coming in and going out. At the point C is coming in and is going out, and the point D also is coming in and going out. At the point A we see what's coming in. We having here flow inflow, that's flow in of the traffic, and flow out of the traffic. Flow in the traffic is this here 500 is coming in, and also 300 is coming in. So having 300 plus 500, and going out is x1 and x2. So 300 plus 500 is equal to x1 plus x2. Let's do the same thing with point B. The inflow is 200 x2 and x4. So we have x2 plus x4 on the left hand side. Right hand side we having here 300 going out and x3 is going out. So we have x3 plus 300. We take point C. Inflow is from north, that is 100 and 400, and going out is x4 and x5. So we get the equation 100 plus 400 is x4 plus x5. Now we will check here at this point where the flow in is from x1 and x5, and going out is 600. So having x1 plus x5 is equal to 600. We write a system of linear equations regarding to this one, where the unknowns will be our values x1, x2, x3, x4. From the first equation we get here x1 plus x2 is equal to 300 plus 500 is 800. Then we have in the second equation x2 plus x4, this x2 plus x4, and that's equal to minus x3. So we're having x2 minus x3 plus x4 is equal to 300. And then we have the fourth equation of point C, we having x4 plus x5, x4 plus x5 is equal to 500. Then we have the last one x1 plus x5, and that's equal to 600. So we get here this system of equation. Unknowns are here. Our unknowns are x1, x2, x3, x4, and x5. These are unknowns. So we write the equation in the system of linear equation in the augmented matrix form and solve it by Gauss elimination method or Gauss-Jordan method, and we get the solution of this one. We're having here 1, 2, 3, 4 equations. Unknowns are 1, 2, 3, 4, and 5. So we're having the leading entries, 4 leading entries, and then we're having 1 as a free variable. We can write our equation. We get here, after solving it, we get here x1 plus x5 is equal to 600. After solving it, we're having x2 minus x5 is equal to 200. Then we're having here x3 is equal to 400, and we're having x4 plus x5 is equal to 500. So as I explained you again, we're having these leading variables x1, x2, x3, x4, and x5 is a free variable. So we can write our solution in terms of x5. So we can write here my x1 is equal to, we can write this equal to, let's here 600 minus x5. I'm having x2, my x2 is equal to 200 plus x5. Then we're having x3, where the value of x3 we're having here is equal to 400. Then we have x4. x4 is equal to, the value is equal to 500 minus x5. So we can say here, they depend upon the value of x5. We say x5 is any real number t, can have any value. But we have the condition on this value, because our x5 can't be more than 600. If it's go more than 600, so it become, if it's more than 500 here because it's negative. So then it's become here the negative value, it must be positive value. It can't be 600 here because it become minus minus. It must not be minus, it must be plus. So we say our t must be less than equal to 500 is the condition on that one. It's not free, can be any real number. T is any real number, but we have a condition, but we're having t must be less than equal to 500. So this is our, we get the traffic flow when we take the value of the x5. Just this is going to control the whole traffic from this point. You can see it here with my x5. This is my x5. This is controlling the whole traffic. The value of this depend, the whole traffic circuit depend upon the values of x5. We get the value of x1, we get the value of x2, x3 is fixed. At any case, when you're having whatever the value is, this value will remain fixed 400 under these conditions. And this value is variable. We can change the value and we can see what the values of x1, x2, x3, x3. The very small example which I have given to you, we can have this the traffic in a whole city, and we can just control this one, taking inflow and outflow at the point, and we get the equations, and we can just calculate at different direction how much traffic will be going to shift. We have in this loop, we have just taken this one x1, x2, x4, and x5 in this loop, and the next t going out. What is going to happen if the flow and outflow is given to us? You can change the outflow, inflow, and these values of x1, x2, x3, x4, x5 will be changing. So this is the idea behind the traffic control, and this is also, again, we're having the big matrices, and we can use our numerical linear algebra to solve these problems.